This is my first video in my module on linear programming, in which we're going to discuss kind of what linear programming is and what it's useful for. So I suppose we'll go ahead and start with this. When we talk about like economics or business analyses, we talk about a lot of the time this word optimization, trying to find like an optimal solution. Okay, and so optimal, this is not necessarily kind of a maximum or minimum type of situation. When we say optimal solution, maybe we need to satisfy a bunch of like given constraints or kind of prior guidelines, but at the same time trying to maybe minimize cost or maximize profit, which is something we'd like to do. So what we do is we discuss and look at the situations that we're talking about and set up a system of typically linear inequalities that kind of describe the given constraints or the kind of the guidelines for the situation. Say, okay, so given that all of these things would satisfy the situation, which one at the same time gives us like an optimal solution? Okay, so here's what I can tell you. In past videos we talked about systems of linear inequalities. We graph them and we find this feasible region. You can see I've got a little image here. This would be like, say, the set of all points x and y that satisfy our given, say, business constraints or economic situation. At the same time, which of these points that would satisfy everybody in our system would give us, say, maybe a maximum profit or a minimum cost, as a couple of examples here. And what I can tell you is this: the nifty thing about feasible solutions is this: if one of these points in the feasible region is going to produce, say, a maximum profit or minimum cost, it has to actually lie at one of the vertices. Okay, so here's what we're going to do. We are going to use our concept or conception of linear systems to say, well, if these are all the possible feasible solutions, which one at the same time, say, maximizes or minimizes what we call an objective function? Okay, so we say an optimal provides an optimal solution to an objective function. Okay, so we say objective function. Okay, so when we talk about objective function, these are, say, functions that will define, that really represent costs or necessarily profit or anything that we're trying to maximize or minimize. But objective functions are typically, you'll see that they're, in this video at least, defined as some like z is like some ax plus by or something like that. But this is the thing we're trying to make as big or as small as possible. But again, I can make you a promise. If an optimal, I say, because every point in the shaded region satisfies each constraint in the system, it's not clear how we would find the point that yields the maximum value of, say, our objective function z. But what I can tell you is this: it can be shown that if there is an optimal solution that would make our objective function as big or as small as possible, it has to happen at one of these vertices of the feasible region. So it means we can find a maximum value of z. And here's how we'll do it. We'll graph the feasible region, we'll take all these points right here, and we'll plug them into the objective function to find which one makes it the biggest. Okay. So there is like a process to this, but we say here are the protocols for solving a linear programming problem. Number one is this: let's just sketch the region. You'll notice up here I've already got some constraints. These are the things that bind our set of possible solutions that make everybody happy here. But I want to sketch the corresponding system of constraints and find the feasible region. But the next thing we'll do is we'll find the vertices of this region. Of course, we said a max or a min must occur at a vertex. And once we find all the vertices, hey, it's really simple. What we'll do is we'll test the objective function at each of the vertices. So you'll also notice up here, I've got this objective function. In this case, we'll work through this first example here. I want to find the maximum value of z, but subject to these kind of like restrictions here, these constraints. Okay. So in other words, which of our points in our solution region or feasible region would make our objective function the biggest, in this case, the maximum value of it? So what we'll do is we'll just find all the vertices and plug them into this objective function, say, well, which one did it? So let's go ahead and start by graphing what we have here, starting with our first constraint, which is x is greater than or equal to 0. This is some vertical line. We would graph x equals 0 first, and it's a solid line because it's greater than or equal to. Now I can tell you this is not true on every linear programming problem, but a lot of the time it is a greater than or equal to or less than or equal to case. So we have this solid line at x equals 0, and of course if we had y equals 0, it would be this horizontal line here, horizontal line right here. Y equals 0, we'll label it y equals 0. Okay, we'll go back and shade later. The next constraints, we say x plus 2y is 4. Let's go ahead and find some intercepts on this. We'd say, well, if I plugged in 0 for y, I would get 4 for my x. So this hits my x-axis at 4. That'd be right here. And it hits our y-axis. If we were to plug in 0 for x, it would hit our y-axis at 2. So we'd say, okay, so it hits at 2. This would be a solid line, be this guy right here. Oops, let's try to make this as straight as possible. There we go, right here. So we get this x plus 2y is equal to 4. We'll label that with an equal sign. Now our next constraint here, we say, well, what's my x-intercept? You notice if we plug in 0 for y, we get an x-intercept of 1. So this hits our x-axis at 1. Interesting thing is if you find the y-intercept, it's negative 1. You know, plug in a 0 for x, you get y equals negative 1. Thing is, my graph doesn't go down to negative 1. So perhaps what we could do with this equation right here is if we needed to, we could list it in slope-intercept form. This would be the same thing as negative y equals a negative x plus 1. And if we multiply both sides by a negative 1 here, we get this. We say y equals, it'd be a positive x minus 1, so a y-intercept of negative 1. So it seems that, yes, I'm still going down here. But we get this solid line that's doing this indefinitely. And of course, I'm drawing this by hand, no straight edge. So we are going to have to do a little bit of algebra here, but we'll label this x minus y equals 1 was our constraint. So now, this is all part of the first step here. We're going to go back and shade our feasible region. What I know is this: if x is greater than or equal to 0, I'm definitely shading to the right of this constraint here. And if y is greater than or equal to 0, I'm shading to the right, or sorry, above this constraint here. In other words, we are trapped in the first quadrant in this instance, okay? All positive x's, all positive y's, or at least non-negative. In the next few instances here, we say, well, 0, 0 is on neither of these next two constraints, so we could plug in 0, 0 into them to see if we get a true or false statement. So in this case, I get 0 plus 2 times 0 is less than or equal to 4. In other words, 0 is less than or equal to 4, and since this is true, for our first constraint that we labeled right here, we would shade toward the point 0, 0, so like down here. And then the next constraint here, if we plugged in zeros, we essentially get 0 is less than or equal to 1, which is also true. So we would shade towards 0, 0, which happens to be above this constraint here. And so we're saying, okay, so first of all, the thing we were in search of is the same thing you always find when you're doing linear systems in the first place of inequalities, is this feasible region. You notice we get this bounded feasible region right here. So like, I wish I would have made it a little bit bigger, but we say what we're looking for the vertices of this feasible region. So, you know, let's make these stand out a little bit, maybe like a lighter blue. This has 4 vertices here. We have a vertex here, a vertex here, a vertex here, and of course a vertex here. So 3 of these vertices are very easy to determine, like 0, 0 is one of our vertices here. This point here, this was the point 2, 0, comma 2 is this point. We have this point over here was another intercept, 1, comma 0. And then we're going to need to solve for this vertex right here. And the interesting thing is, just to solve for this, we'll just solve a system of equations. So we already know this is the point where these two graphs intersect, the x plus 2y equals 4. That was intersecting with this graph that we labeled here, x minus y equals 1. So solving this system, let's see, we have x minus y equals 1, x plus 2y equals 4. If we were to double the first equation, use the elimination method and wipe out our y's here, we would get this equation, 2x minus 2y equals a 2. And when we add these cancel, so we get 3x equals 6, so x equals 2. And not only does x equal 2, if we plug this back into one of our original equations here, we get 2 minus y equals 1. So let's see, a negative y would equal a negative 1, so we get y equals 1. So what this means is, this is the point, x value is 2, y value is 1. Okay, so now keep in mind with linear programming, here's the deal. We want the feasible region, but the reason why is because we wanted to find the optimal solution for this objective function. And we said this optimal solution, it's got to happen in a vertex, okay? So what we're going to do is we're going to make what we call an optimization table. And here's how this works. We're just going to put our vertices on the left, any vertex of the feasible region, and we're going to talk about our objective function on the right. And our objective function is 3x plus 2y. So here's how this works. We'll just take all of our vertices, 0, 0. We had the point 0, 2 was another vertex. We had the point 1, 0 was another vertex. And last but not least, we have the point we just found, 2, comma 1. So our job here is to just plug this in, each of these into our objective function here, and see what you get for a z value, or the value of this function that, say, could represent, in this case, I don't know, profit. Maybe, I don't know. So if you plug in for x and y here, 0 and 0, we get z equals 3 times 0 plus 2 times 0. In other words, we get z equals 0, which is definitely not a maximum if I'm going to compare it to these ones here. But if I plug in 0, 2, so I'd be 3 times 0 plus 2 times 2, we get 4. Plugging in 1, 0, we get 3 times 1, which is 3 plus 2 times 0. So we still get 3 plus 0 is 3. And last but not least, 2, 1, we'd say, all right, well, 3 times 2 is 6. 2 times this y value of 1 is 2. So 6 plus 2, 8. So we would say this, and this is really important. We have a maximum value of 8. And that is not the same thing as answering this question. And where did it occur? And it occurred at the point 2, 1. Okay, so to ask you where does it occur at and what is the maximum value are two separate questions. But this is essentially what we do when we're doing linear programming. So we're going to throw in another example here in the next video. So tune in.